Okay, so hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate in the Material Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or tutoring, then check out the links in the description below. Okay, so we're going to get started on the first set of questions now. Oops. Okay, so the first question asks, which of the following aqueous solutions are good buffer systems and why? So we have potassium hydroxide and potassium bromide. Let me just write down, before I go through all of the different options, I'll just write down what does make a good buffer system. So good buffer systems can be any of the following. So you can have a weak acid plus the salt of a strong base. Or you could have a weak base plus the salt of a strong acid. And then lastly, you can have a weak acid plus a weak base compound. Okay, so now I'll go over all the different options that they give us. So first we have potassium hydroxide, which is KOH, plus potassium bromide, which is KBr. So potassium hydroxide is a strong base, but KBr is also a strong salt. So both potassium and bromide are considered strong. So therefore this would not be considered a good buffer system. So let's look at hydroiotic acid plus sodium iodide. So the hydroiotic acid is an example of a strong acid. But again, the sodium iodide is an example of something that would also give off two strong salts. So we can't use that as a buffer either. Okay, so next we have ammonia, which is NH3, plus ammonium nitrate. So this is NH4 and then NO3. So the ammonia is an example of a weak base. And then our ammonium nitrate is an example of how you'd get a salt of a strong acid, which is the NO3. So therefore this one would be considered a good buffer system. Let's look at our other options anyways. So you have hypochlorous acid, is shown there, plus hydrobromic acid. So they're both acids, but the first one is a weak acid, and this is just a strong acid. So we can't use this as a buffer system. And then lastly, calcium bromide. Plus barium bromide. So these are both salts of strong acids and strong base. So this also can't be used as a buffer system. So let's look at the answer from our junior tutor. So in order to get buffer solution, we need to use weak acid plus its salt of strong base. And then they give examples. Weak base and its salt of strong acid, or weak acid plus weak base compound. So that's what I said as well. And then they also selected just ammonia and ammonium nitrate as the good buffer. For the examples, so potassium hydroxide, strong base, potassium bromide, strong salt mixture cannot act as a buffer. Hydroiotic acid and sodium iodide, strong acid, strong salt mixture. Hypochlorous acid, hydrobromic acid. Here these two are acids, it cannot be a buffer. And lastly, calcium bromide and barium bromide. These two are salts of strong acid and strong base, it cannot be a buffer. So this solution is correct. Okay, so on to question number 2. Determine whether each molecule given below is polar or nonpolar. Let's write down the definition of polarity. So polarity arises due to the separation of electric charge. So this leads to dipole moments. And usually this happens when like one side of the molecule is slightly positive and the other side is slightly negative. Okay, so let's look at the options they give us. So for A, CF4. Let's draw that out. We have our carbon in the middle, and 4 fluorines attached like this. So let's just write some like notes about this. So fluorine is more electronegative than carbon. So if I were to only look at the bonds on their own, you'll see that since fluorine is more electronegative, the dipole moment goes towards the F. So its bond is polar, but if we look at the molecule as a whole, all these fluorines cancel each other out. So the bond is polar. But CF4 molecule is nonpolar. Okay, so let's look at the next molecule they give us, PBr5. So this looks like following, where you just have the phosphorus in the middle, and then again all the bromines kind of stick out like this, and again they all cancel each other out like that. So this is a non-polar molecule as well. Okay, let's look at the third one. Xenon F2. So here, there's going to be some lone pairs involved. But if I draw out the fluorines, they still cancel each other out like this. So this molecule is also nonpolar. And then lastly, D, SF6. You get the same effect over here, where they all just cancel each other out. So this is also a nonpolar molecule. So these are all examples of nonpolar molecules, but I guess I'll just show what a polar molecule would look like. So we can do everyone's favorite, which is water. So you have a more electronegative oxygen and lower electronegative hydrogens. So this side has a slightly positive charge, and the side with the oxygen, which is more electronegative, is more partially negative. So this would be an example of a polar molecule. Okay, so let's see what our junior tutor said. So it looks like they were given different molecules all together, but the answer is correct, what they said. You can see, so this molecule is an example of a polar molecule. If you were to have 2 chlorines on one side and then 2 hydrogens on the other, then you have a dipole moment going towards the chlorines. So this is a polar molecule. And then here we have another polar molecule. So I'm just gonna verify with the molecules that were given in the question. In this question. So all molecules are nonpolar in this question. The theory in the solution is correct only. Okay, so solution is incorrect. Okay, so let's go to question 3. Phosphine, pH3 gas, decomposes according to the equation. The kinetics of the decomposition of phosphine at 950 K was followed by measuring the total pressure in the system as a function of time. The data to the right was obtained in a run where the reaction chamber contained only pure phosphine at the start of the reaction. So choose the rate law that describes this reaction, and then calculate the value of the rate constant and choose the correct units. Okay, so let's write down the reaction of the phosphine. Okay, so given the units there, I'm gonna make just like a rough graph of the time versus the pressure. Sorry, this is smaller than I thought. So this is obviously not to scale. It's just so that we can kind of estimate the rate of the reaction. So this is pressure. And then on the x-axis is going to be time. And then if I were to plot these values, so 0 and 100, 40, 151, 80, 168, we can see that there is a linear expression that occurs. And when you have a straight line going up, this means this is a first order reaction. If we're looking at the rate, first order rate. So for the first one, where you talk about the rate law, for first order reaction rates, it's going to be the following, where rate is equal to K H3. Okay, so we can see that the more phosphine we have, the higher pressure that we have goes up as time increases as well. So it goes up in a straight line. Okay, so next, I'm just going to write down everything that we know. So bear with me while I do this. So our P initial, which is the pressure that we had at the beginning of the experiment, is 100 torr. And then I'm just going to take one of the values at a given time. So I'm going to look at the pressure after 40 minutes, and that is equal to 151 torr. But you can use any given X or Y values. And then I'm also going to write down like the expression I would get if I wanted to calculate P total. So for P total, this is the pressure of your initial minus 4x. So for x, I'm just going to denote as pressure. And the 4 comes from the reactants. So it's going to be 4x plus x plus 6x. So what this means is that as the decomposition reaction occurs, we're going to have 100 torrs, and then subtract what we started with, which is our reactants. And then we're going to add pressure that is from our products. So 1 is from this P4, and then this is from the 6H2. So then I can simplify this further just by doing P total is equal to P initial plus 3x. Okay, so we can solve for x. I'm going to use a different color. So let's say at 40 minutes, the pressure in the system is 151. So this is equal to 100, which is what we started with, plus the 3x. And then I'm just going to solve for x. And you're going to get 17 torr. Okay, so from here, I can now calculate the concentration of the phosphine at 40 minutes. So this is going to be our initial minus the 4, and then I'm going to sub in 17. And then I'm going to get 32 torr. So now, since we know that we have a first order reaction rate, I can use the following equation. Okay, so this is the kinetics equation that you would get since we want to calculate K, which is our rate constant. And now I can just sub in all the values that I found. So for the pressure of the phosphine at 40 minutes, it was 32. The pressure initially was 100. E negative 40K. So this is the 40-minute mark and then K. And now I'm just going to solve for the rate constant. Okay, so I'm going to take the ln of both sides in order to get rid of that E. So ln of 0.32 is equal to negative 1.139. And then I got my K value as 0.0285 inverse meters. Let's see the answer that the junior tutor said. So the given reaction is an example of decomposition, and we prove that all decomposition reactions and nuclear decays are first order reactions, so that part is right. And then they do the same kind of unknown pressure thing that I did as well. They got x is equal to 17. Okay, so they calculated for the pressure. The total pressure of phosphine at T equals 40 minutes is equal to the 100 is minus 4 times 17, so they got 32 torr. And then they solved for K. So they used a different equation, but it's pretty much the same thing. Yeah, they just simplified it and then subbed in the values, and then they got the same K value of 0.0284-ish. So this solution is correct. Okay, so let's go on to question 4. Predict the organic product of the following reaction. Include hydrogen atoms in your structure. So let's try to guess. See what kind of product we would get if we had a double bonded carbon. And then each has its own methyl group. And then it reacts with HBr. Okay, so if we were to do that, let me write out the mechanism. So you can have your double bond attack and deprotonate the HBr. And then as an intermediate, you have this carbocation. So that means it's a positively charged carbon. But then the Br can come back. Since it has a minus charge, and come up and try to neutralize that carbocation. Then we're left with this final product. So let me rewrite it here. And this is called 2-bromobutane. Okay, so this is the electrophilic addition of H2O. Oh. So looks like a different reaction than the one that's given, but the mechanism is similar. Yeah, so this time they form the same kind of carbocation group, and instead of the bromine coming to attack the positive charge, it's actually a water molecule coming in to attack, and they were left with an OH group instead. So this mechanism is correct, but for this question in particular, it is not the right answer. So let me just write down what it should say. So the Okay, so I have that the double bond deprotonates HBr, forming a carbocation intermediate. The Br- neutralizes the positively charged carbon, forming 2-bromobutane as the final product. Okay, so on to question number 5. Complete the following sentences about DNA packaging. Some terms may be used more than once. Okay, so let's look at all our options: histone, DNA molecule, heterochromatin, nucleosome, and urochromatin. Okay, so I'm just gonna fill in the blanks here. So the less condensed form of chromatin is blank. Okay, so this is euchromatin. Next, the inactive form of chromatin is blank. So the answer for this one is heterochromatin. Next, a core composed of 8 blank proteins interacts with DNA through hydrogen bonding and ionic bonds. Okay, so the only option for the proteins is histone. So we know that it's going to be core composed of 8 histone proteins, interacts with DNA through hydrogen bonding and ionic bonds. If DNA structure is described as beads on a string, a bead is a blank. Bead is a, and then the answer for this one is a nucleosome. Okay, so on to the next sentence. The more darkly staining form of chromatin is blank. So for this answer, it is also heterochromatin. So this one is similar to the beads on a string, but this time the string is the blank. So the string is your DNA molecule. And then lastly, a blank is a DNA protein complex, a nucleosome. So a nucleosome is a DNA protein complex. So let's look at the answer that our junior tutor said. The less condensed form of chromatin is euchromatin. The inactive form of chromatin is heterochromatin, core composed of 8 histone proteins. The bead is the nucleosome. The darkly staining form of chromatin is heterochromatin. And then if DNA structure is described as the beads on a string, the string is the DNA molecule. And then lastly, a nucleosome is a DNA protein complex. So this solution is correct. Okay, so well done. Okay, so let's go on to question number 6. The density of solid, let me write this down. It's question number 6. So the density of solid chromium is 7.15 grams per centimeter cubed. How many atoms are present per cubic centimeter of chromium? As a solid, chromium adopts a body-centered cubic unit cell. How many unit cells are present per cubic centimeter of chromium? Okay, so let's write down everything that we know. We know the density is equal to 7.15 grams per centimeter cubed. I'm gonna write down the molar mass of chromium as well. So this is 52 grams per mole. This can be found on your periodic table. So the first part of the question is asking how many atoms are present per cubic centimeter of chromium. So every time a question asks you, or every time a question has atoms involved, or particles, or photons, we know that we're going to be using Avogadro's number. I'm going to write that down as well. Avogadro's number is equal to 6.022 times 10 to the power of 23. And the units are atoms per mole. So you can see that it's a very large number. So that's how many atoms are in 1 mole. Okay, so next, for part A, all we have to do is to solve for the atoms. So all the units need to cancel out somehow. So I'm going to write down atoms are equal to the 7.15 grams per centimeter cubed. And then I'm going to multiply this by Avogadro's number. And then that will be divided by the molar mass of chromium. So it was 52 grams per mole. So then if you pay attention to the units, they should all cancel out. So grams will cancel each other out. These moles will cancel each other out. And then for the number of atoms, all you have to do is plug that all into your calculator, and you should end up with 8.28 times 10 to the 22. And then the units are now in atoms per centimeter cubed. Okay, so next let's look at part B of this question. As a solid, chromium adapts a bodied centered cubic unit cell. So first let's write down what a BCC unit cell looks like, just so that we can all kind of picture it. It's also always really bad at drawing these, but basically you have your cube. And then these are all of the atoms in each corner here. So you can see that each corner contributes 1/8 of an atom. And also in a BCC unit cell, you have a single whole atom in the middle here. So therefore I can say that there are in total 2 atoms per unit cell. I'm gonna do the math where it's just 1 atom plus 8, 1/8 atoms. Okay, so since we know that there are 8.28 times 10 to the 22 atoms per centimeter cubed, I'm gonna take that value and then I'm gonna multiply it by 1 unit cell for every 2 atoms. And then you end up with 4.14 times 10 to the 22. And then the units are unit cells per centimeter cubed. Okay, so let's see the answer of our junior tutor. In a body-centered cubic solid, each unit cell contains 2 full atoms of the compound. And then they have the same kind of math, so 1/8 times 8 of the atom at each corner equals 1, and 1 full atom at the center equals 1. The mass of 1 chromium atom is 52 AMU. And then this is equal to 8.63 times 10 to the negative 23. The mass of 2 chromium atoms is twice that, 1.73 times 10 to the negative 22. Since the density must be the same, we can say volume 7.15 is equal to 1.73 times 10 to the negative 22. Which gives 2.42 times 10 to the 20. The edge length of a unit cell is the cube root of the volume, which is 2.89. So it doesn't look like they answered how many unit cells are present per cubic centimeter of chromium. And they also don't give the number of atoms present per cubic centimeter of chromium. They just they calculated for like the edge length of a unit cell. So I'm just going to summarize what I just did. Okay, so I said by multiplying density of chromium with Avogadro's number, then dividing by the molar mass of chromium, the number of atoms per centimeter cubed is 8.28 times 10 to the 22. Since there are 2 atoms per unit cell, therefore there are 4.14 times 10 to the 22 unit cells per centimeter cubed. So solution was incorrect for that question. Okay, so next it says to rank the following nitrogen-containing aromatic molecules in order of increasing basicity. Okay, so this is question number 7. And basically, when you have something that is the most basic, this means it's more likely to accept a proton. Okay, so I'm just going to write down all the molecules that they give us so we can go over each of them. Okay, so it's easier to first compare this pyridine with the pyrrole molecule, which is this orange one. So basically your pyrrole molecule is the least basic. And the reason for that is if this accepted another hydrogen, it's gonna disrupt the conjugation of the ring, and it's actually gonna be less stable than how it is right now. I'm just gonna write that down. So I wrote that adding another hydrogen breaks the conjugation of the ring, so it's already stable since it's aromatic. Okay, so now I'm just going to look at each of the pyridine molecules that have either a Ch3 group or a bromine group. So let's look at the Ch3 group first. So Ch3 is an electron donating group. So basically this is going to be more basic than just pyridine on its own. And then on the other hand, let's look at the bromine. So bromine is an electron withdrawing group. It's kind of like the opposite of the CH3. So it's more unlikely for the lone pair on nitrogen to accept a proton. So therefore this is less basic than the pyridine. So now let's rank the compounds. So from 1 to 4. From least basic to most basic. The least basic is the pyrrole. And then secondly, it's the pyridine group with the bromine. And then third is just normal pyridine. And then the most basic is the pyridine with the CH3 electron donating group. So let's see the answer from our junior tutor. Least basic is pyrrole, then the bromine, then pyridine, and then the CH3 group on that. So the answer is correct. Okay, so let me just do that. And I think we have time for one more question. So classify each of the following as a Lewis acid or Lewis base. Let's write down the definition of a Lewis acid. So basically, a Lewis acid is an electron pair acceptor. And typically these molecules have multiple bonds between atoms. Also, all positively charged ions are Lewis acid. And also, they tend to have empty d orbitals. That was not a straight line. So on the right side, let's write down the qualities of a Lewis base. Basically, they are electron pair donors. All anions, so all negatively charged anions, are Lewis bases. Finally, they have at least, or they can have at least one lone pair. Okay, so let's look at our options here. So first we have carbon monoxide. So this is going to be a Lewis acid. You'll see that there are multiple bonds between the atoms. Then aluminum trichloride is also a Lewis acid. So that's because it has vacant orbitals. For the bromine, it is negatively charged, so I'm going to put that in the Lewis base side. Same thing for the hydroxide ion, it's a Lewis base. So NH3 is also a Lewis base. It's because this nitrogen has a lone pair. Fe2 plus is positively charged, so it is a Lewis acid. And then finally, carbon dioxide can also be a Lewis acid. Okay, so I think that is all. Let's see what the junior tutor said. All cations are Lewis acids. A molecule's central atom contains complete octet are Lewis acid. So all molecules that have where the central atom contains a complete octet are Lewis acids, okay. And then multiple bonds between atoms of dissimilar electronegativities are Lewis acids. Okay, so they added a bit about how the atoms have to be of different electronegativities. All anions are Lewis bases. A molecule's central atom contains lone pair of electrons are Lewis bases, so that, yeah, at least one lone pair. And then they wrote it out. They have this is a Lewis acid, Lewis acid, Lewis acid. I don't know where the Lewis bases start, but I guess it starts here. So it's kind of partially correct. I'm just gonna say that correct, but CO. I think carbon monoxide is gonna be one of those molecules that can act as both a Lewis acid and a Lewis base. So I'm just gonna say that it's still correct. Can act as both the Lewis and Lewis base. Okay, so solution is correct. Okay, so I think that's all for today. So if you enjoyed today's Q&A and you'd like to be notified of when we do this next, then please hit the subscribe button and notification bell below. And if you'd like to submit a question of your own, then check out the links in the description. And also, if you like the video, go ahead and give it a thumbs up and leave a comment. And just don't forget to share this video with all your friends and classmates. So this has been Donna from OneClass, and I hope to see you soon. Bye.